Welcome back, guys. So this is the next part of the series of lectures on rotational motion. And in the previous parts, in the first lecture, I described about the generalization of the concept of rotational motion using angular motion. And in the second part, I described about the angular equations of motion. And in the third part, I described about the relationships between the translation quantities in translational motion and quantities in rotational motion. And then I described the special terms period and frequency and how they relate with the angular velocity of an object in rotational motion. And so we have come to the fourth part of this set of lectures, and in this lecture I introduce a special term which is the moment of inertia, which is very relevant to the calculations that you see in rotational motion, and it's very relevant to the problems and the examples, and also it is very important in using whenever you are faced with the concept in rotational motion. So moment of inertia. Alright, let's start. So far I have used the concepts in rotational motion along with the concepts in translational motion. So in this part of the lecture also I will use the concepts regarding the moment of inertia and its derivatives and the other things which are relevant, other quantities which are relevant to this topic, with the use of the translational motion, or with the end of the explanation from translational motion. So I'll take a simple example from translational motion. I will call the translational motion linear motion. You can simply take it as translational motion. Linear motion. I'll take an object like this. Frictionless piece of frictionless surface. Okay. V equals 0. I reduce the concept of friction in another video. I'll take an object of mass m, which is either it is at rest, u equals 0, either it is u in constant position where u equals v. So according to Newton's first law, for this object to move, you should have an external unbalanced force acting on that object. Put an external unbalanced force F. And, however, since this is frictionless, it's okay, but if it is friction, if it has friction, as soon as you put F, the object will not move. But in this case, the acceleration of the object is A. You can write from the second law, X equals A, Y equals since mass is constant, so acceleration is directly proportional to the force difference. Right. So now you consider a book like this. A book goes on object that is placed on the table. This book has mass zero, but this book will not move because this book has something called inertia. Or it's the force that is reluctant to any object has inertia. But if the force you put it, say you have an object like this, mass 20 kilograms, you put a force F say 1 Newton. So from F equals ma, this is frictionless, F equals ma, 1 equals 20 times A, so A is equal to 1 upon 20 or 0.05 meters per square second. So this is the acceleration. So this is a very small acceleration that sometimes you will not even notice that the object is small. But if you put a large force, this object is 20 kilograms. If I increase the force up to say this 1 Newton, so I take it as 15 Newton. Right? This is 15 Newton. So F equals ma. So F equals to 15, mass equals to 20, and the acceleration is 0. So A is equal to 15 by 20, which is 3/4 of 0.04. So this is about 15 times faster, 15 times larger than the acceleration, 15 times the acceleration that we observed in applying a new force of Newton 1 here, 0.05 meters per square second, and when applying a force of 15, this acceleration is proportional to the force. The acceleration should also be 15 times the acceleration observed. Right? So, what happens here is that any object has a simple head inertia, reluctant to move, but as the force, see, all these surfaces are frictionless, and as the force increases, the object has to move. Object moves, but if you put even 0.0 infinitesimal force is 0.0001 into 10 to the power say -7, it will move, but you can see a specific acceleration. Right? You can see a specific acceleration. But when you increase the force, it will have some acceleration that you can see. So if A is equal to 0.75, within 10 seconds, it will have a velocity of about 7.5 meters per second, and we will have a displacement of about 75 meters. So 75 meters is a huge distance for an object within such a small force, 15 newtons. You can move this object 75 meters. But in this case, you will move about 5 meters. Yeah, 5 meters. Exactly 5 meters. Right? So, how is the force? So, now you see the force acceleration is directly proportional to the force applied. But in the case of inertia, the object is reluctant to move. If you increase the force, object has to move. That was what I wrote here. Okay, here. Object has to move. So object has to move means I didn't mean that the object doesn't move under this circumstance, but the object moves in both circumstances, but the observed distance traveled is greater. So we have more force, we have more capability to win the moment of inertia, win the inertia of this object in translational motion. And the inertia of an object depends only on the mass if it is traveling in a linear path or in translational motion. Only dependent on mass. But in the case of rotational motion, as I described in the first video, first concept is the motion in which an object moves around a fixed point. So, object moves around its axis. Rotational motion. It is the object. This is the axis. This is called this axis of rotation. Since this is spherical, so this is a spherical object, and if it is viewed 2D, in 2D, it's a circle. Since this is spherical, if you change the axis of rotation here, and you draw another axis of rotation, going through its center, it will be the same. It will be the same means, say I take a small part of this out. The mass in it is dm, and the distance between this point, the center and this mass, the center of mass of this point is Rm, right? Is Rm. And if you take the same distance, if you draw a circle with Rm, this is spherical shape, this is Rm. This is R, which is the radius of the object, Rm, and this is place. This is the part that I selected. This is dm, which is mass dm. So the correction of parts of dm will make the whole mass n. So the Rm, the radius of the, not the radius, the distance between the center of the object and the particle I have selected, this Rm, does not vary if I select this mass, the center of mass lying on the same circle. Say, I take a point here, right? Take a point here, which also has radius Rm, also the distance Rm, and center of mass. Here I take a part like this, take another part, Rm, take a part like this. Doesn't mean, so the distribution is important. The distribution lies to see. The distribution lies to see. Right? However, if you take a cylinder like this, cylinder or cone or plane or something that is not spherical, or is symmetrical, somewhat symmetrical, if I take the axis of rotation, this is the center of the top surface, this is the center of the bottom surface, and this is the center of mass or the center of gravity. If I take an axis going through all these points, it will take an axis like this. So this is the axis of rotation 1, I will take AR1, right? If I take another axis going through the center of mass but not through the two centers, but perpendicular to the line I have drawn above, I'll take as AR2, and if I take some mass like this from some point, and I will take this as x, m, and the mass dm, so in this case, as in the above case here, and if I draw a circle like this, what happens? Does that mean this? Does it mean that the mass of this one is equal to this? This may be equal to AR1. AR1. If you take AR1, it may be equal. But if you take AR2, it's not equal. If you took AR2 and draw some mass like that, it will certainly not lie in the circle. It will be sometimes out of the circle, or it will be sometimes inside the circle. So the distribution of mass, the distribution of mass on two axes is not the same. It's the same in some cone or something like that. So we take a cone, we take a rod, right? This is AR1, we take this as AR2, we take this as AR3, and the rod I take this as AR1, we take this as AR2. right? So it's not the same. It's not the same. So what I have to tell you is that the distribution of mass, if it is rotating about its axis, rotating about its axis, rotating about its axis, right? The distribution of mass is also important in rotation because the distance between two masses which have the same mass and the same distance varies according to the axis you take. Although it's not relevant in an axis which has say something like a sphere or something like a circular shape, as in this example, it means the same. But if you take some object like a cylinder, as a short cylinder, a cone, a rod, a ring, a wheel or something like that, the axis of rotations, when you change the axis of rotations, the mass distribution changes. The mass may not change, but the mass distribution, the distance to such a mass, they say that the magnitude of the mass I took is 20 grams from that position, the distribution of that mass. To get a 20 gram distribution from two axes of rotations in such a shape, I have to take two distances. Say we take 20 gram mass from this object, from the center of gravity we take about 10 centimeters. But if you change the rotation, if you take the axis of rotation, you have to travel either less than or more than 10 centimeters. And in the sphere, it's the same. Right? In the sphere. So, in rotational motion, not only the mass distribution is also important in defining inertia. So, we call the inertia in rotational motion as moment of inertia because it depends on both the mass and the distribution of mass. So I'll take a simple shape like this one. And I will take the axis of rotation which is outside. This should not be true because axis of rotation